In this video, we're going to look at what happens in the case of small values in the internal cells of 2x2 contingency tables. The correction we're going to use to calculate the chi-square for a 2x2 contingency table is given in 8.5, and it's called Yate's correction. Yate's correction can be used only for 2x2 tables and cannot be used for 2x3 or 3x5 or any other size contingency table. The calculation of Yate's correction is very much like the calculation of a standard chi-square, except that as the formula in 8.5 indicates, 0.5 is subtracted from the absolute value of the difference between the observed and expected before that value is squared. So to look at the calculation of Yate's correction, I will copy the data, paste it here, and call this expected. And as we did in the other video, the value in this first cell will be equal to the B column total times the 2 row divided by the grand total in D4. And again, fix the D4 with $2 signs using F4. The D2 will be fixed with a dollar sign in front of the D, and the B4 will be fixed again using F4 with a dollar sign in front of the 4. And when I copy this to each of the other cells, I have all of the expected values. Now, in order to calculate the chi-square, I'll again copy this and paste it here. And I'll call this Yate's for Yate's correction. And following the formula, this will be equal to the absolute value of the observed minus the expected minus 0.5 hat 2 divided by the expected, which turns out to be 1.36. And if I drag this to each of the other cells, I will get the chi-square values for all of the cells using Yate's correction. Now here I will create the chi-square. It is again the sum of the internal cells and the probability, and that is equal to CHI DIST. X is the chi-square value and 1 degree of freedom, and the probability is 0.027. What would have happened had I not used the Yate's correction? Let's copy this and paste it here. And here I will again say that this is equal to the observed minus the expected squared divided by the expected. And instead of getting 1.36 as the result, I get 1.77. And if I drag this again to the other 3 cells and now copy this and paste it here, I get a chi-square value of 6.3 and a probability of 0.01. Essentially what the Yate's correction does is to make the chi-square test more conservative. It makes it so that you are less likely to reject the null hypothesis of independence. What would happen if we changed the 5 to a 6? Now, we definitely would not reject the null hypothesis of independence with these observed data given the Yates correction. We also would not reject the null hypothesis of independence given, this needs to be changed to standard, given the standard calculation, but we are very much closer to rejecting that null hypothesis, that is to a probability less than 0.05, than we are here.